All right, welcome everybody. Welcome in. So continuing with our discussion of chapter 4, last time we kind of talked about a review of exponential and log functions and log properties. And then today we're looking at the calculus portion of those. I'm not sure how long chapter 4 is going to take us to talk about today. I was thinking it over. I don't really want to get into chapter 5 yet. I think it would be best, I think we're best off talking about chapter 5 next week. I just don't want to get too far ahead, and then I'm talking about material way before people are ready to work on it, and then you'll start to forget it by the time you get to it, and then, you either have to watch the video again, or you just skip it, and then it's extra hard. So I think it's best if we don't get into chapter 5 today. So we'll kind of see where we fit with chapter 4. We'll kind of see how much time that takes us today. But chapter 4 is important. You are, assuming that you're going to be going into something where you're going to use this stuff, it is highly likely that you're going to be having to deal with the derivatives of logarithms and the derivatives of exponentials. Now, it is the case that it's more and more likely when you go forward that if you have to do this stuff in the workplace, you're probably going to have some software that helps you out with it, right? There's already software that can be helpful with derivatives. But again, as always, the important thing is knowing how to use it, right? That's great that you have something that you can put a function into and it gives you back the derivative. But if you don't know what that means or how to use it or any of that kind of stuff, then what was the point of any of it, right? So we'll look at some examples of that today, and we'll go over that. So your homework on Chapter 4 is due the 17th. We will wrap up Chapter 4 today, Thursday the 13th. Homework's due on the 17th. We will spend next week talking about Chapter 5, probably the whole week talking about Chapter 5. Maybe at the end we'll get into Chapter 6. And then we'll talk chapter 6 and then get ready for the exam and all that kind of stuff. I know it moves so fast in the summer. So let's see. I'll wait a little bit longer to take roll. I think we'll probably have a few more people dropping in, but we'll go over that. I do want to mention, I'll probably mention this again at the end of class. So if for some reason you were not able to take the exam last week, right? I had this growing list of people who for seemingly legitimate reasons we're not able to take the test. You need to get in there and take it. It will not be extended past this week, so make sure you get in there. Some people missed it. We had a few people get COVID and so legitimate medical reasons. Some people had work problems. So get yourself in there, get that test taken care of. We can't really extend stuff. We're kind of coming up to the end of the semester or the end of this course, and things are going to happen fast enough already. So we're not going to be able to push things back any further than they already are. So make sure that last day to take the test then is tomorrow. So make sure you're making contact with the testing center if you need to. And remember, they are remodeling the testing center right now. So Thursday and Friday, they will be in LRC 128 and 129. So if you're in the LRC and you're not sure where those rooms are, because I think I might know where those rooms are, but I'm not 100% sure. Ask around. There's people in there who can point you in the right direction and help you figure out where it is that you need to go. Okay. I did do drops the other day, so students got dropped. So I think I might have one more student that I'm watching to see if they're going to show up. And then maybe drop that student. But by and large, I did most of the drops. I forget if it was Monday or Tuesday that I did the drops that I needed to do. So I know some people were a little bit nervous about that because you're not sure exactly what I meant about who I would drop. Mainly, I dropped students who clearly were not participating in the class anymore, right? Or they were far enough behind that a drop is better than the F that they would eventually end up getting. So, if you're still in the course, you're probably good. Unless you've missed a few classes in a row. Oh, this is the wrong roll. That's the morning class. Thought there was one in here. Oh. Better look at that. There's one or two more people that might get dropped, but again, if you're participating and you're actively doing homework, and you're showing up to class and doing what you're supposed to do, don't worry about it. You'll be fine. Okay, we'll get to that in a few minutes. So we are talking about logarithms and exponentials, and specifically taking derivatives of those things. So taking the derivative, it's the same problems that you've been doing throughout the semester. So, we've used the derivative to find rates of change. We've used derivatives to find equations of tangent lines. We've used derivatives to do different word problems, and sometimes we've done derivatives just to do derivative problems. Those can include the chain rule and the power rule and the quotient rule and all that kind of stuff. So basically, you're still going to be doing all that stuff, but sometimes when you're doing it, you're also going to have to keep in mind how to take the derivative of a logarithm or the derivative of an exponential. So just keep that in mind. We'll do some problems like that where, you'll start off with some problems where it's like one and done. You do the one step of taking the logarithm and then you're done. Then we'll look at ones that involve chain rule and also the exponential as well. So it's like the simpler problems, and then we'll build up into the more difficult ones. And, all these topics that you've looked at previously, you're basically going to have homework problems where you revisit those, except it's including the logarithm and the exponential that you have to try to figure out how to go through and find the derivative of. So with that, let's take a look. Let's go into 4.3 here. That's differentiating the natural log function. So you should hopefully remember there are numerous different logarithms, right? You can have log base 2, you can have log base 7, you can have log base 3.5. You can have all sorts of different bases for your logarithm, but it's very convenient to use the natural log in many, many circumstances. So oftentimes we do exactly that. So you'll find that we generally stick to, in these settings, the natural log. Okay, so let's take a look inside the book here. That's what I was trying to do. All right, we got it. So I know I was going to start with the exponential function, but usually they're taught in a different order where you take the derivative of the exponential and then they teach you the log. This book does it in an opposite order, and I can't quite figure out why. I almost wonder if it was a mistake, but I just want to keep in the same order of the book so that I'm not confusing people unnecessarily by skipping around, right? So the derivative of the natural logarithm function. So remember, d dx just means we're going to take the derivative with respect to x. Let me make that even a little bigger. We're going to take the derivative with respect to x of the natural log function. So this is telling us that the derivative of the natural log of x equals 1 over x. So that's pretty easy, right? You have a problem that says the natural log of x, you're told to take the derivative, it becomes 1 over x. Okay, that's not bad. Okay, so that's pretty straightforward. But then you can see we start getting into things like, okay, well, what if we have a product rule here? Because notice this function is a product rule. So we'll kind of do that separately. I've got this over here. We'll do, actually, let me move this out of the way. So say we want to find the derivative. Of, let's say find the derivative of f of x when excuse me, when f x equals 7x cubed times the natural log of x. So we want to find the derivative of the function f of x when f of x is equal to 7x cubed. Oh, what's wrong here? I don't know. The software is having some kind of error there. What's the problem? Okay, weird. Looks like it's okay now. So find the derivative of f of x when the function f of x is 7x cubed natural log of x. So notice we've got that natural log of x sitting there. So we know when we get to the point where we're going to have to take the derivative of the natural log of x piece, we already know what that is. That was given in the problem right here. The derivative of natural log of x is 1 over x. But we can't just dive into that yet. We have to consider the larger problem that we're working on. And the larger problem that we're working on is really a product, right? 7x cubed and natural log of x. Those are the two things that are being multiplied that we're taking the derivative of. So remember, that's the derivative. You leave the first function alone times the derivative of the second plus the derivative of the first function times the second function left alone. It's that product rule that we're used to. So let's look at how that would work. So if we look at 7x cubed, we're going to break this up as 7x cubed and natural log of x. So first we'll leave the 7x cubed alone. So we've got, I'll kind of do it this way, 7x cubed times, now the derivative of natural log of x is 1 over x. That's the new thing that we're learning. Plus, now we take the derivative of the first piece, 21x squared, and then we leave the second function alone, natural log of x. Why am I? Oh, because I keep not leaving a space there. Okay, that should work. Okay, so is everyone clear with what I did? This is just the product rule, but this piece, this 1 over x, that came from when we took the derivative of the natural log of x. That became 1 over x because of our new theorem that we just looked at. Okay, and then that's the new thing, right? That's all there is. Now it's just a matter of simplifying the same way you've been doing so far in this class. So let's see, what would our next line become? So this would become 7x, so looks like we have a fraction. We're going to have 7x squared over x plus 21x squared times the natural log of x. All right, remember the space that time. Oh, wait. Oh, okay. I messed up. There's a typo. Yep, thanks. I noticed it right. I was seeing this wasn't coming out right like I thought it should. Thanks. There's a typo in here. I wrote 7x squared when this first piece should be 7x cubed. Yeah, thanks. Thanks to the people in the chat who noticed that. Looks like I had a typo. Right, so that we leave the first function alone, 7x cubed, times 1 over x, the derivative of natural log of x. Then we take the derivative of 7x cubed, giving us 21x squared, leaving natural log of x alone. And then this simplifies to 7x cubed over 1 over times 1 over x plus 21x squared natural log of x. And then we're getting, so 7x cubed over x is just 7x squared plus 21x squared times the natural log of x. Now, here's the thing that they do. You see this especially in this class, the applied calculus class, or the business calculus class is basically the two names this class goes by, where they factor at this point. So you're going to see them do this on the homework, and you might go like, wait, where did that, like you say you get to this line, and then when you look at an example in on the homework or the answer that that they're showing you how to arrive at in the video or something, and you start seeing that it's factored, sometimes this throws students and they go, wait, why does their answer look so much different than mine? It's because they're factoring it, right? So what we would do is look at this term and say, well, what's in common? It looks like they both have a 7x squared in common, so let's factor that out. So 7x squared times the quantity 1 plus, so we're going to have 3 times the natural log of x. So in this, especially when you're dealing with these problems, when you see this, if you look at that last line and you're like, wait, what? I got the line before it. How did they get that one? It's just that they're factoring out the greatest common factor, which in this case is 7x squared. So they're factoring that thing out, okay? And then you would put that in the homework. So you can see, like, for here, for this first homework problem, is this 743? Yeah. So if I look at the answer, see how you end up with 6x cubed and then it's in parentheses 4 natural log of x plus 1? It's a similar problem, but you can see what they've done. You can see that they factored the version. They factored the 6x cubed out the way that we did here. So that's the form they wanted in. So just recognize that, I guess. Okay. And now, of course, we can always evaluate this at a certain point if we need to. We can find the equation of the tangent line. Remember back when we were finding equations of tangent lines, you would use the derivative to find the slope at a certain point. That was the slope of your line. And then you would use the point that the tangent line goes through in order to figure out the intercept of the line. So you could do the same thing here, right? It's all those same questions that were being asked about derivatives. It's just that now you had this added complication of a new derivative that you didn't know how to take the derivative of 15 minutes ago or 20 minutes ago. And it's just the derivative of natural log of x is 1 over x. Okay. So that's helpful. So I want to make this clear to people. When we look at this rule here, the derivative of the natural log of x is equal to 1 over x. It's a very easy derivative to find. But there's the issue here is that rarely in real life, when you're dealing with a logarithm, is it just the natural log of x, right? You don't run across that very often. It's not rare to run across it, but more often than not, it's going to be some other version of the natural log, right? Not just natural log of x, maybe the natural log of 2x or the natural log of x squared or something like that, right? It'll be some version of the natural log of something else. And so some of you are probably already starting to recognize, oh, that means we're dealing with a composition. That means we have to use the chain rule, right? And so that's where we're going. We're basically going to build on this right here and come up with something that's more complicated. So that's what this next one is. This is the chain rule for logarithmic functions. So what is this saying? This is saying if we take the derivative of y with respect to x of the natural log of g of x. In other words, the formula that I just gave you a few minutes ago was just straight up natural log of x, right? Nothing complicated, nothing fancy. this is the natural log of g of x, meaning that we have some other function embedded inside of our natural log. So it could be the natural log of x squared, the natural log of x squared minus 3x plus 4, right? You've got some other function inside of your natural log, and you're trying to take the derivative. But remember, if that's a composition, then that's where we're supposed to bring out the chain rule. And that's exactly what we're seeing here, right? When you take the derivative with respect to the outer function, what is that outer function? It's natural log. So the derivative of that would just be 1 over g of x. But then using the chain rule, we have to multiply by the derivative of what's inside. And that's where this g prime of x comes from. So I know sometimes people get overwhelmed where they're like, man, we have so many formulas we have to memorize. And I would say you shouldn't be memorizing most of these formulas. This one, you'll kind of know it by the time you do enough of these problems, but you should be able to think your way through it where you go, oh, well, this is just the chain rule. So my outer function, the derivative will be 1 over x, in this case 1 over g of x, and then you multiply by the derivative of the inner function, which is g of x. I don't know why I keep getting blurry over here. Let's see. There we go. Okay. So let's take a look at, well, we'll use this as our example, and I'll just explain how this is working. So there's a nice pattern that occurs here. Sometimes people call it the logarithmic derivative because it's the derivative of the logarithm, but sometimes it shows up in other places as well, but people call it that. So let's say in this case, notice we don't just have the natural log of x. We have the natural log of 5x squared plus 2x minus 7. So it's not, the derivative isn't just 1 over x, right? That was that really just that basic natural log of x, take the derivative, you get 1 over x. Here we're taking the natural log of 5x squared plus 2x minus 7. So think about the chain rule. When you take the derivative with respect to the outer natural log function, you get 1 over whatever's in the parentheses, okay? Because the derivative of natural log is 1 over x. So we treat that as the outer function. Okay, and then the chain rule piece says we multiply by the derivative of the inner function, which of course in this case ends up being 10x plus 2. And then we could think of this 10x plus 2 as being 10x plus 2 over 1. So when we do the multiplication, we just end up with 10x plus 2 over 5x squared plus 2x minus 7. Okay, so that, let's see, not quite on screen there. So that's just our derivative right there. So when you're doing the derivative of the natural log of something, it's real easy. Basically, you're going to end up with a fraction where the thing that's inside the parentheses becomes your denominator. We can see down here. And the derivative of what's inside the parentheses becomes your numerator. Right? So it's one of those, I know like the first time you see it, it can seem confusing, but once you've done like 3 of these problems, you'll be like, okay, I get it. The function goes in the denominator, its derivative goes in the numerator. And it's also easy to understand. You don't have to memorize that. You just go, well, it's just the chain rule is all we're really using at that point. Okay. Oh, right. So what if we have this? So what's different about this problem? How is this different than what we were doing before? Well, the difference is that now it's not just natural log of something in parentheses. It's natural log of something in parentheses being cubed. Right? So see how we have another layer of that chain rule? We have a very outer layer, which is the natural log. Then we have the next inner layer, which is to cube, and then we have the innermost layer, which is x squared minus 4. So it's like those 3-step chain rules. Oftentimes we have like a 2-step chain rule where you take the derivative with respect to the outer function multiplied by the derivative of the inner function. In this case, we're looking at 3 steps. There's 3 steps to our composition. Okay. So let's do this one. Let me write this one up. I think this will be a little bit easier to do this way. And like many problems, there's more than one way to do this. So in the book, they're actually showing you 2 different ways to do this problem. Okay. So basically, we're going to work from the inside, well, I should say from the outside in, right? So find this when our derivative is So let me move this over a little bit. Okay, so find the derivative of f of x when f of x is equal to the natural log of x squared minus 4 cubed. So think about the order in which you would do this. Like if someone just gave you this function, right? Not even talking about the derivative. Someone gave you this function and said, evaluate this function at f of 2. Or say, we won't go through the steps, but let's just say they wanted you to evaluate the function at whatever, x equals 5. The first thing you would do is you would stick a 5 in here and then square it. And then you would simplify what's in here. Then you would cube it. And then you would take the natural log. So if you think about the order in which you're following to evaluate the function, that gives away which functions are the inner functions and which ones are the outer functions. Basically, the inner functions are the steps that you would be doing first. The outer functions are the steps that you would be doing last. Okay, so the chain rule tells us we're supposed to start by taking the derivative of the outside and work our way inside. So when we go to do that, we would end up with, okay, well, the outermost function is the actually let's see, which way do I want to do this? Let's do it this way. So remember, we have a log rule that says we can bring that 3 down in front. So we're going to get 3 times the natural log of x squared minus 4. Right, that's one of our log rules, the log property, the power rule. We can bring that exponent down in front. So remember also, when we go to take the derivative, we can ignore that constant that's out in front. It's the same thing when we take the derivative of a polynomial term. We get to ignore the coefficient and just multiply it in the end. So in this case, if we want to take the derivative of this, we've now been able to take this 3-step composition, right, that would involve the chain rule, and we've reduced it to 2 because we were able to use intelligently the log properties. So this would become then 3 times, so now we're going to need a fraction because the thing that's going to go in the bottom of in the denominator of the fraction is x squared minus 4. And then I'll just put a 1 there for now. We'll write this out so that everyone can see what's going on. Then we have the chain rule piece, which is going to be 2x. Well, really this 3 and this 2x can go into the numerator, right? Because this is really 3 over 1, and this is really 2x over 1. So when we combine all that stuff together, we actually end up with 6x over x squared minus 4. So 6x over x squared minus 4 is the derivative of that function. So that's kind of the easiest way to do it. Use a log property to reduce it. Let's look at the other way to do it, which would be to keep using the chain rule. So here what they do is they take the derivative with respect to the whole thing, which makes it 1 over that stuff. But then we have to use the chain rule. So we take the derivative of the inner function, which is x squared minus 4 cubed. But in order to take the derivative of that, you have to use the chain rule again. So this is leaving it as that 3-step composition. So when we take the derivative with respect to that piece, the 3 comes down in front. We decrease the exponent by 1. The inner function stays the same, but then we multiply by the derivative of this inner function, and we get 2x. And then sort of rounding everything up, you get this, which then again simplifies to 6x over x squared minus 4. So it's either way that you take that derivative, you're going to get the same answer. Okay. Here's a problem where you're using your quotient rule. Let's see. Is that what we want to do here? What was this one? Actually, it looks like what they did here was to turn this into 6 times natural log of 8x squared to the negative 1 and then go from there, which makes it a little bit easier. You see you have an implicit differentiation problem. So we go through and do that. There's a natural log in here. But like, don't worry about it. If you've already done implicit differentiation. So it's going to be it's the same stuff you were doing before. It's just that along the way when you're carrying out that implicit differentiation, you're also going to run into some logarithms along the way, and you just want to make sure that you can calculate those, okay? So here's the example in the book if you want to look at that. It's a good one to look at. It's basically, you already know how to do it. It's just involving some logarithms when we do it. Okay, let's take a look at, let's look at the homework problems. Let's see. Yeah, this one is done well. I like how they do that. Sometimes it's not clear, but see how they're making it clear that this function is the natural log. Because if this outer set of parentheses isn't there, sometimes people wonder, like, wait, are we cubing this or are we cubing the whole thing with the natural log? Even though it's sort of implied you're cubing the input. But this makes it very obvious. That second set of parentheses makes it unmistakable. You're cubing that entire input, right? Yeah, all of these should be able to be done like the problems we looked at. This one, you're probably going to want to rewrite that square root in terms of the exponent 1/2. Once you do that, it should just sort of fall into place. When you get to the implicit differentiation one, just kind of follow along that problem in the book. Again, there's nothing special here. You're just doing the implicit differentiation that we learned in that previous section, but you have a natural log in it. But it doesn't really change much. Find and interpret the derivative. Here, just state whether the derivative is correct or incorrect. Here they have a cost function. Here, this question 13, just marginal cost. Remember we talked about marginal cost? It's the derivative of the cost. So basically your goal here is to take the derivative of this function, and then you'll have the marginal cost, and then you answer question 13. Yeah, so So those are all pretty straightforward. So I know that probably seems weird because people get intimidated by the natural log. But once you start doing those, you're going to realize like, oh, it's just like these examples. It's just like the thing he showed us in class. Like some of these other chapters have lots and lots of variations, but for these problems, there's not nearly as many. Let's see, that was the logarithm. So let's look at this one. And I talked a little bit about this one, and then I had to end up ending class a couple minutes early. But this one's nice because the derivative of e to the x is e to the x. So when you run across e to the x and you have to take its derivative, it's real easy. The derivative of e to the x is e to the x. Now be careful, it's kind of like the derivative of the natural log of x being 1 over x. This is like the simplest case. Usually in the real world, you don't just run across e to the x being the function that you're trying to take the derivative of. It's usually something more complicated. But it will at some point break down to like some of the steps that you have to work on are taking the derivative of e to the x, or knowing that that's the derivative, and then you can carry that out. So for instance, let's do this one over here. Let's look at this problem. So we want the derivative of 8x cubed e to the x. We'll move everything over a little. Okay, so find the derivative of 8x cubed e to the x. So when I look at this, it's kind of like the problem we did at the beginning of the chapter on, or the section on logarithms. Is you look at this and go, I don't know, that looks an awfully lot like a product rule. It looks like I have two different functions that are multiplying each other. They're both functions of x, and they are multiplying each other. So I want to go ahead and take the derivative of that thing. Okay, so if we leave the first piece alone, we get 8x cubed. Let's put it in parentheses. And then we leave the second piece alone, e to the x, plus, now we're going to take, I already left the first piece alone. Okay, so it's the first piece left alone times the derivative of e to the x, but the derivative of e to the x is e to the x, right? That's the new thing that we're looking at. Now we're going to take the derivative of the first piece, so that's going to be 24x squared. And then we're going to leave e to the x alone. Okay, so it's just your product rule. Leave the first piece alone, 8x cubed, take the derivative of e to the x, which is e to the x. Take the derivative of the first piece, which is 24x squared. You bring the 3 down, 8 times 3 is 24. Decrease the exponent by 1, 24x squared. And then leave the e to the x as it is. Okay. Now, again, they're going to want us to factor out everything that we can. That's like a common thing for, especially in this chapter, right? You'll see it in some other chapters, but especially in this one. So let's see. What can we take out here? Well, it looks like there's an 8x squared e to the x. Yeah. So 8x squared e to the x. That term is common to both of these, so we can factor that out. So that's going to be 8x squared e to the x. So when we factor that out of the first piece, we're left with an x. When we factor that out of the second piece, we're left with a 3, and we're left with 8x squared e to the x times x plus 3. Now, if you're looking in the book, you'll see that they get the terms just in the different order. I have x plus 3, they have 3 plus x. But it's the same exact thing, right? It's the same, like x plus 3 is the same as 3 plus x. So you get the same either way. The only difference is the way in which they implemented the power or the product rule, but it ends up being identical. So don't worry about that. All right, let's do this one since it's been a while. Find the equation of the line tangent to the curve f of x equals 7x e to the x at the point 0, 0, rounded 2 decimal places. Okay, so let's take a look at what that would look like on the graph. So what do we have? F of x equals 7x e to the x. 7x e to the x. We can see this is what that function looks like. And we're concerned at the point 0, 0. So let's get that point on there. 0, 0. So we've got our function, we've got our point, and we want to find the line tangent right there. So remember, when we go to create our line, we need two things. We need a slope and we need an intercept, right? Because remember, we've got this, we've got, here's your, you've got your slope, changes the slope of the thing. You've got your intercept, changes the intercept. So we need to figure out both of those. So we can kind of see it's going to be somewhere around in that vicinity, right? Somewhere like that. We'll see what it ends up being as we work it out. But that's the idea. We need to figure out the equation of this line. So we need a slope and intercept. When you do these problems, you always figure out the slope first. And great news, we have a tool, a calculus tool, which is going to help us get the slope of that line. It's the derivative. So we need to figure that out. So let's work that through. So if we want to find the derivative, we want the derivative of 7x e to the x at the point 0, 0. Okay. Well, this is going to involve the product rule, right? So just basically like the problem we were just doing. So let's see. If we leave the first one the same, we're going to get 7x times the derivative of the second. Well, the derivative of e to the x is e to the x. Now we take the derivative of the first piece, which in this case is going to be 7, and then we leave the second piece alone, so we get e to the x. Okay, so that's our derivative right there. Now we can clean that up using the kind of factoring that they like to do in this part of the book. So we will make that. Let's see. It looks like we can pull out a 7e to the x. And that's going to leave us then with what? X plus 1? Yeah. X plus 1. So there's our derivative. It pops up here. So this is our derivative. And we want to evaluate it at the point 0, 0. So at the point 0, 0, our x is 0. So if we evaluate this at 0, we get 7e to the 0 times 0, times 0 plus 1. Right, so I just took this function. We're evaluating it at an x value of 0. So what do we have then? Well, 0 plus 1 is 1. And 7e to the 0, well, e to the 0 is equal to 1. So 7 times 1 is 7. And then 7 times this one is 1, times this one is 1. So it looks like the whole thing comes out to 7. Okay. So that's our slope then, right? So basically we know that the line that we want to deal with, we're looking for a line that's of the form y equals mx plus b, because it's a tangent line, so it's a line. But we already know it's going to be y equals 7x plus b, right? So then the thing that we're missing that we have to do in order to solve for b is basically plug in the x and y of the point that we care about. We need to plug in the x and y from a point that's on the graph, but we already saw the point on the graph that we care about is 0, 0. So that's the point. This point is, we get it from the curve, but we also know that the tangent line is going to go through that point. So we use that point that the tangent line just comes up and barely touches on the curve to solve for our y-intercept in the problem. So that part's easy, and especially in this problem, we're just going to plug in 0, 0. So that is going to become 0 equals 7 times 0 plus b. So it looks like b is going to be 0. B is 0. So now we know that b is 0. So if we come right back up to here where we knew that y was equal to 7x plus b, that must mean that y is equal to 7x plus 0. But we don't write equations of lines as y equals 7x plus 0. We would write that as y equals 7x, right? So let's take a look if that works. Y equals 7x. We can look at it visually, although we should definitely change the color here. How about orange, green, purple, green. Okay. And if we zoom in, that sure looks like a legitimate tangent line. We've got the red curve, we've got the blue dot, and we've got the green tangent line going right between it. So it sure seems like that's the right thing. Okay? And it is. That's our line that goes through there. So you can see every step I just took was the same as what we did before when we were finding equations of tangent lines. The only difference is that now I did it when we first figured out what that derivative was, it involved an exponential. So we had to use the exponential to figure out what that was, right? Okay, now is a good time to take roll. So let me see. Let's see what we got here. let me check one thing here. I just want to make sure my records are right. Give me 1 minute. Okay, good. Okay. Okay, good. A couple things occurred to me, and I had to make sure the roll was right because I had to double check that people are in the class who are supposed to be in the class and that people who aren't supposed to be in the class aren't. So I just had to double check that. Thank you. And we'll put that. We don't need that for now. Okay, so like I said, I did most of the drops. This class is pretty good about students participating overall. The people who are still around are largely participating, so that's good. Didn't have to drop too many people from this course, but I do have to keep taking roll. Okay, let's see. What do we got? Trey, yes, I got you, Trey. You're good. Okay, thanks everyone for making that easy. Did I get that person? I did. Okay. Okay, great. Then back to this. So differentiating the generalized exponent. So again, most of the time that you run across e to the x, it's not just going to be e to the x all by itself. It's going to be e to some function of x. That is, it could be a polynomial, or it could be, it could be anything, but it's some other function of x that you're raising that thing to. So, it could be the derivative of e to the 3x squared minus 4x plus 5 or something like that. So, again, it's just chain rule. You don't have to worry about these being some kind of big new fancy thing. You're applying the chain rule, and that's really what it comes down to. So, for instance, we've got e to the 3x squared plus 5x. So you can see what we're doing. We take the derivative with respect to the outer function, but the derivative of e to the x is e to the x. So when you take the derivative with respect to the outer function, you just get the outer function back. You get e to the 3x squared plus 5x. That's his first piece. But then you have to remember the chain rule piece, which says to multiply by the derivative of the inner function. Well, the derivative of the inner function is 6x plus 5, right? The derivative of this polynomial right here. So that's how we get e to the 3x squared plus 5x times 6x plus 5. And then they just do that normal. In fact, in this case, there's nothing to even factor, right? We just, they like you to write the 6x plus 5 piece in front. And it's really already factored for you. Let's see, question here. Let me double check. Juliet. Sorry, Juliet. Oh, okay. Glad you said something. I got you now, Juliet. Okay, good to go. Okay, so that's what I'm saying. Like, look how much writing there is here. There's not really much writing to take the derivative of a problem like this. It's real easy to do. Hey, take the derivative of the outer function, multiply by the derivative of the inner, you're good to go. Now here they start mixing it up. Look here, we've got natural logs and exponentials mixed together. That's okay. It doesn't really matter. Like we looked at, so for something like this, the natural log for the outer function, it's going to be 1 over this thing. So that's where this piece comes from. It's just 1 over the inner function times the derivative of the inner function. Well, the derivative of 2x will be 2, so that's where the 2 comes from here. And then if you want to take the derivative of the outer piece, it's the outer function times the derivative of the inner function. So this looks like a lot, right? If you look at all this, let me shrink it down here so you can see like the whole problem at once. It looks kind of complicated, right? It looks like there's a lot going on. So there's a lot of ink being put on paper in this case, but there's not actually like that much stuff that's going on that's very complicated. It's really just using the chain rule and knowing what the derivative of a log is and knowing what the derivative of an exponential is. And if you've got those two things, you're good. Okay. The second derivative, now this one, let's see, this one's actually not too bad, but they start to get a little messy. Right, you could see that as you were taking more and more derivatives, and if we continued to even take a third derivative, then this one would get kind of nasty. But as is, it's not too bad. So let me just kind of guide you through how they did this. So if you go to look in the book, you can follow along. For your first derivative, or is this the same one we just did? E to the 3x squared plus 5x. Nope, I guess they changed it slightly. So we want to find the second derivative, so f of x is e to the 2x squared plus 5. So you take the derivative of that, and you get e to the 2x squared plus 5 times the derivative of the inner function. Well, the derivative of the inner function is just 4x, so you get 4x e to the 2x squared plus 5. Now, that was the first derivative, but they're asking for the second derivative. So notice now it's going to be a little bit more complicated because while we started with something that was easy to take the derivative of, now we have a product, right? Now we have to take the derivative of a product, 4x e to the 2x squared plus 5. Now we have to use the product rule. So you can see them using the product rule. It's not real hard. It's just that it's more complex than the first step that we did, which was actually really simple, right? Simple does not mean easy. It just means there wasn't a lot of steps to the first part. The second part is more complex, but it's not too bad. And then you end up with the second derivative. I wouldn't really want to sit around and take the derivative of the third derivative, so the next derivative, but it wouldn't be the end of the world. It's doable. Let's see. We had someone else coming in here. Okay, Isabella, I got you on the roll. You're good. Okay. Same thing here. Now we got a few things going on. Let's see. We got a product rule going on. 6e to the negative 7x, that's one piece. Natural log of 4x, that's the other piece. Go through, do your product rule, work it all out. It's not that bad of a thing. All right, then we have, so 7's kind of a pain, right? So what are they doing? This is, remember where we use the quotient or the difference quotient? So we're using the difference quotient here, and you can see, oh no, actually we're using, sorry, I was thinking of a different problem. We're using the quotient rule here, right? So it's that this is that complicated formula. This one's the one that's a little harder to remember for most people. So you've got the top function times the, let's see, bottom function times the derivative of the top function minus the top function minus the derivative of the bottom function all over the bottom function squared, right? And then you just have a whole bunch of simplifying to do, which is kind of a pain, but you eventually end up with your formula. So nothing too complicated in that case. In this case, they're just kind of giving you a shortcut, but I don't even know that it's necessarily like meaningful. Like you know how to do chain rule, so don't worry about it. you're good. Here we see the function being used in a way that is actually sort of business related. So at this point, I think you can probably do the math. It looks like we may even start chapter 5 here, or at least start talking about it for a bit. But before we get too far, I want to talk about, at least explain this kind of application problem so that you understand how you would use this stuff in the real world. So the resale value R in dollars of a particular type of laser cutting tool T years after its initial purchase is approximated by the following. So R of T is equal to 450,000 E to the negative 0.27 T. So what do we want to do? Find and interpret the rate at which the resale value is changing. Now just think about it for a minute. What kind of function do we expect to see? Would you expect to see an increasing function or a decreasing function? Well, when you buy a machinery, in this case a laser cutting tool, does that machinery usually go up in value or down in value? Right? And you can think about it in terms of, well, what if I was going to buy one? Would I rather buy a new one or a used one? Probably a new one, right? So the old ones lose their value over time because the demand is for, the preference is to get new ones. So what is the decay rate? Well, that's just our derivative. If the function is telling us the resale value, then the derivative would give us the rate of change of that resale value. So you can see in this case they're giving us an exponential function. You can see how easy it is to take that derivative. We've got our original function here, 450,000 e to the negative 0.27 t, and then the negative 0.27 in front, that's the chain rule piece coming in there. So then you would just multiply negative 0.27 times 450,000 to get this. Sure enough, looks like we've got a decreasing function like we would expect. Thus, r prime of t is equal to this. And then you just plug your values in, and here they give you your interpretation, right? So there's nothing tricky going on there, nothing fancy. Here we've got a drug in the bloodstream. When they inject you with a drug, generally what happens is it takes a few minutes for that drug to kind of spread throughout and sort of take effect. So it kind of goes up for a little bit, and then it peaks, and then it starts to wear off and starts to come down. So that's why, 40 years ago, like if you were in the hospital, they would come in and, every once in a while and give you these big shots of medication. But that was kind of hard because you would get these big rises and drops in the medication. So what happened is part of the time you didn't have enough medication and you were like in pain if it was pain medication. And then other times when it was peaking, there was so much in you that you just felt sort of like weird and drugged out, right? So what they try to do now is give you more medicine like a little bit at a time. So they get you into that zone where it's actually killing the pain, but you don't feel like you're all drugged out. And they just try to give you enough to kind of keep you right in that zone, like the zone where you're not in pain, but not where you're like all, under the influence and stuff. So that's why these kinds of problems can be very important. For nurses, figuring out that kind of stuff can be very helpful. And it's the same problem as we were doing. You're just finding a rate of change. So instead of rate of change of the price of the machinery of a laser cutter, it's just the rate of change of concentration of your blood, the bloodstream, the medication in your blood, right? Yeah, and then we're there. So usually people do pretty well on these sections. Derivatives of logarithms, derivatives of exponentials, people kind of do okay with that. So hopefully you're able to get through the homework without too much difficulty. It's definitely important that you be as caught up as you can be. So those of you who have fallen a little bit behind, this is a great opportunity where we're doing a chapter here that's not crazy hard to try to get yourself caught up, because it's going to be very difficult as we close in on the end of the semester and you're studying for the exam and trying to do all that to finish up homework if you're behind at the same time. So because I can't extend the anything past the end of the course. We're not really supposed to do that. Plus, there's a lot of pressure on us to get grades in immediately, like immediately, because there's a lot of things depending on those grades, right? There's financial aid under certain circumstances needs to know if you passed the class or not. Many of you, if you're taking this class, you're either at university right now or you're about to be at university, and they're going to want those transcripts so that you don't feel like you have to take it again. You can say, nope, I took this class. Those transcripts can't go out till we get grades in. Some of you are going to want to sign up for the next semester of this course, which, by the way, is only offered at Moore Park in our district, because there's not that many students who need the second semester of this. If you're one of them, look at Moore Park. So because of that, we're supposed to get grades in fast. Like as soon as this class ends, we start getting automated emails telling us, like, hurry up and get grades in. Hurry up and get those grades in. So we can't extend anything at the end. You got to be caught up. Whatever your homework grade is at the end of the term, that's what it is. So if you find yourself with a little time in the next week, you might want to work ahead and work on that. Okay, so we got through that faster than I thought. I kind of forgot. I guess I was thinking there'd be a little bit more complicated problems in there, but they weren't too bad. So let's just start a discussion about chapter 5 so I can give you a kind of heads up about where things are, and then we'll see where we finish today. So chapter 5, like I mentioned, probably the heaviest chapter in this entire course. There's a lot to it. Like every single section in here is almost like it could be its own chapter almost. Like not quite, but close to it. They definitely don't, like they a little bit feed into each other, but each one of them is a very big separate topic, right, from the previous ones. And we had some chapters that were like that, but these are all like huge topics, these 6 topics that we're looking at. And the first one's not too bad, and it starts to kind of set the stage for the rest of this chapter. So yeah, I think we're fine if I start 5.1 today and we go through that. So there's a new symbol. Let me go ahead and open the ebook. Notice that this section, 5.1, is called anti-differentiation. So you learned a thing called differentiation. That's what we've been talking about too so far in the course. Everything up to this point, I mean, we started with limits, but then we used limits to talk about derivatives, and we've been talking about differentiation. Differentiation means you're taking the derivative. Well, what we're going to start doing is basically doing it backwards. We're going to go the other direction. So in other words, we've been having a function f, and you say, what would the derivative be? Right? Here's a given function f, find the derivative, find f prime, find d dx, right? It's all different ways of saying what's the derivative. Well, what if we asked it from the other perspective? What if we said, what's the function that has this thing as a derivative? Right? So basically we were working backwards. It's one thing to know the rules to take the derivative. Now we got to start thinking in the other direction. And I know that probably sounds silly. Like, what? Are we just coming up with extra complicated problems just to give the calculus students something to work on? And the answer is no. This is actually very, very important. So we want to be able to find the antiderivative. So let's look at the definition of the antiderivative, and then I'll try to break it down so that you can actually understand what this is saying. So this is saying the antiderivative or integral. That's a word we're going to start throwing around a lot, is the integral. We're going to talk about integration. Basically, calculus is broken into 2 big pieces, right? No matter what, when you start calculus, the first thing you learn is the limit, because as you're going to see eventually in this chapter, the integral is based on the limit as well. So remember how the definition of the derivative has a limit in it? So does the definition of the integral when we get to it. But there's a few different forms of integrals. So you want to be careful about that. That can be a point of confusion for people. We have a definite integral, and we have a thing called an indefinite integral. And then we have the antiderivative. And these things are all very closely related, and they are easy to mix up. So when you're doing this, make sure that you're paying attention to kind of understand the difference a little bit between these things. So suppose that, notice how they're using a capital F here. Suppose that capital F of x and lowercase f of x are two functions such that f of x, lowercase f of x, is the derivative of capital F of x. Okay, so that sounds confusing. That's a notation that is very standard in calculus. If something is the derivative, you use lowercase f. If something is the, like we can think of it as the parent function, it is the thing whose derivative is little f of x, then we call it capital F of x. Okay? So in other words, we're saying if you take capital F of x and take the derivative, you get lowercase f of x. That's the relationship right here. So, and that's very consistent in calculus, right? It would be very strange for someone to do it the other way around. We always want the capital letter to be like the parent, and then when you take the derivative, you get the lowercase function. So then we say that capital F of x is an antiderivative or integral of lowercase f of x. So it's kind of like, and not exactly, but it's kind of like an inverse function, right? When we talked about inverses and when you've done inverses in your previous classes, we're working backwards to figure out the inverse of the function. But there's a problem with antiderivatives, right? Like, so for example, let's do this. Let's say find the derivative of f of x equals x, let's do 2x cubed minus 4x plus 8. Okay, find the derivative of f of x equals 2x cubed minus 4x plus 8. So hopefully everyone's looking at this and going, well, that's super easy. We already know how to do that, right? But that's the point, is that you know exactly what you're going to get, right? When we take the derivative of this, we get, let's split screen. Yeah, that still works. That'll work for me. When we take the derivative of this, we get that f prime of x equals, so f prime of x is equal to, okay, so we're just going to do our polynomial derivative, right? We should all get the same exact answer when I say find the derivative of this. We should all get that this is 6x squared minus 4. Right? 6x squared minus 4 is the derivative of this thing. We all get the same answer. We're all in agreement about what's going on here. Okay, well, think about it the other way. What if we ask this question from a different perspective? What if I said, for the derivative f prime of x equals 6x squared minus 4. So this time we're starting with the derivative. Find capital F of x. So starting with the derivative x squared minus 4, find capital F of x. And remember, that means we want to find the function whose derivative is little f of x. So I'm saying find the derivative, or find the function that when you take the derivative, find the function capital F of x, that when you take its derivative, you get this thing, 6x squared minus 4. Well, there's a problem with that. And the problem is that every one of you could come up with a different answer. In mathematics, we say that that problem is not well defined, right? A well-defined problem means that every time someone does that problem or a different person does the problem, you should get the same answer. This problem is not well-defined because if I say find a function whose derivative is 6x squared minus 4, we could come up with numerous different values. For example, capital F of x could be the problem that we have at the top of the page. So 2x cubed minus 4x plus 8. We already know because that was part of how we just did it. So when we... What's wrong now? What's the problem? Oh, the autocomplete was putting dollar signs where they shouldn't be. Okay, so we know that if we take 2x cubed minus 4x plus 8 and I take the derivative, I get 6x squared here, I get minus 4 here, and this goes away. Okay, well, is there another function that would give us that same derivative? How about this one? How about this? 2x cubed minus 4x plus 2. Does that give us 6x squared minus 4 when we take the derivative? Yeah. How about if we take this one, minus 3? Yeah, that one's going to give us that same derivative, right? It's going to give us 6x squared minus 4. So you're probably starting to figure out there is an infinite number of these different capital F of x's that we could come up with, all of which are going to have a derivative that is 6x squared minus 4. We could literally spend forever doing this because there's an infinite number. You just come up with a different constant on the end of that function. And you might go, oh, well, is it really that different? Well, if you graph these, yeah, you'll see they're different. In fact, let's do that. Let's change this problem here. Let's do, for example, x squared minus 5, x squared minus 1, x squared plus 3. We're seeing all these different functions. These are just these functions just differ by a constant, x squared minus something. So what does that make them? If we think back to our translations, that makes them all vertical translations of each other. They're the same function, but just shifted up or down. And yet they all share the same derivative. Okay, so that would appear then that functions that differ by a constant share the same derivative, and they all end up being vertical translations of each other. So what we do then, instead of asking this question about, well, what function has this as a derivative, we just describe the entire family of functions, and we group them all together, because then we know it's any of these infinite parabolas right here shifted up or down. They're all going to have a derivative of 2x. Right? The derivative for all of these, we could make up lots more versions. The derivative would be 2x. They all have that. So when we say if we want to find capital F of x for a problem like this, the way we describe it then is by saying we want that capital F of x is equal to 2x cubed minus 4x plus c. Plus c, this capital C. This is a big deal. This is a place where you can miss a bunch of problems on the test. Every time you miss plus c, you're going to miss a point, right? So, and that's the next test you take will be partial credit, right? You'll get partial credit. But if you forget the plus c, like that's a place where some students forget, and then you miss it like 12 places on the test. That's 12 points right there, right? So you want to be careful about that. Make sure you're writing the plus c. Sometimes books write it with a small c. It doesn't really matter. The point is it's just some constant, because anything that's of the form 2x cubed minus 4x plus some constant, and it could be a negative, so it could technically be a minus like this one, those are all going to have a derivative 6x squared minus 4. Yeah, so there's a good question. Kyle's asking, could it be written as negative c? Yeah, mathematically it would be the same thing. People would think it was kind of weird that you were writing it that way, and it would be sort of unnecessarily confusing. But you could, because you know, when it's plus c, your c can be positive or negative. So you're really adding or subtracting. So if you're subtracting, your c can still be positive or negative. It's just something that's sort of considered poor form. It's like how we don't write x to the 1 and we don't write x to the 0. We simplify those down. Writing plus c is just considered a little bit more simplified, even though, yes, writing negative c is still mathematically correct. It's just not good form. Yeah. Okay, so you can see there's an example in the book. They have here, they take anything of the form 2x squared minus 5x, and they're getting 4x minus 5 for all of those derivatives in there. So we would say these all belong to the same family. And you can see here they're just saying it's 2x squared minus 5x plus some constant. And here we see the picture again. This is a different family, but they're all vertical translations of each other, right? So then we get what's called the indefinite integral. So remember, there's different types of integral, so we have to be kind of careful when we use that word integral. And one of the things about this chapter is every time you think that you're getting comfortable with the word integral, we're going to throw something new at you. And then you're going to go, wait, I'm confused again. I thought I understood it, but now I'm all confused. So we'll take a look here. Suppose that capital F of x is any one of the infinitely many members of the family of antiderivatives of f of x. In other words, we're talking about all those vertical translations of each other where they all just differ by a constant, and they're vertical translations. And when you take the derivative, you get the same thing for all of those. That's what they're talking about in this sentence. Suppose that capital F of x is any one of the infinitely many members of the family of antiderivatives of f of x. That's what they're talking about. And here's this new weird notation we're going to use. There's this symbol, which I'm not sure how well it's showing up. It's kind of that symbol you see on a violin sometimes. It's like an elongated S. Actually, it's a stretched out S is originally why they chose this, because as we'll see later in the chapter, we can think of this as a sum. That is, we add things up. So the letter S is kind of where that symbol, why they chose that symbol. Don't worry too much about that. We'll get to it later. But if you've seen the cover of or the front of a violin, or it's got a weird curve, that's what that symbol is. In the homework, you can see it as well. See it right here, this symbol. You'll see it a little better when you look at the homework. But that's the integral symbol. Okay. So we read this as the integral. So the integral of f of x dx is equal to capital F of x plus c. Okay, so there's a lot of notation there, and it's really important notation, but it's confusing. So let's try to break that down. So first of all, this dx, for now, just think of this dx as telling us which derivative which variable we're integrating with respect to. Okay. Those of you who go on to take the second semester of this class, that's the multivariate calculus. You'll have like sometimes an x and a y, and sometimes it matters the order in which you integrate. So you have to figure out, wait, am I supposed to integrate with respect to x first and then integrate with respect to y? Or am I supposed to integrate with respect to y first and then integrate with respect to x? And it can be a little confusing. So that's why we write the dx there. It helps tell you the order. However, in this class, we're only doing single variable calculus. So the variable here should generally match the variable over here. I don't remember off the top of my head. I don't think we do any problems. I don't think we do anything that's multivariate in this class. Certainly don't cover it in depth, but I don't think we have even any problems that come up where we have to worry about that. So the dx, just think of it as, oh, this is telling me that we're doing this with respect to x. So you've got some function here. This is our capital F of x. So this capital F of x, if you were to take its derivative, gives you lowercase f of x. That's how you think about it. And see the plus c out here? That's like here where we had all these, where instead of writing -5 and -1 and +3, we just write plus c because it captures all of them. It captures the infinite number of functions, which are vertical translations of each other, and all have derivative 2x. That's what this is telling us, is we can just, like in this case, we would just write it as x squared plus c. Those are all the functions that have derivative 2x. Anything that's written x squared plus c has derivative 2x. So that's what this means, right? And this is the indefinite integral. You want to make sure you're getting comfortable with that, because next week we're going to learn about the definite integral, which is, it seems very different, and then we end up connecting them all and finding out they're related. That's why they have the similar names, because although they seem like completely different topics, the fundamental theorem of calculus ties them all together, and you go, oh, these things are actually all related to each other. That's one thing that's tricky about this chapter, is each section seems like it's a total diversion and has nothing to do with anything else, and then all of a sudden in the end you bring it all together and go, oh, it's kind of all the same thing. But it's definitely not obvious at first. So where c is an arbitrary constant, although it's weird they use little c down here. I think that's a typo. They should have used capital C. The function f of x plus c is called the antiderivative or indefinite integral of f of x. So you can say either one of those, antiderivative or indefinite integral. One thing that can get confusing is once people start getting comfortable with this, they'll just use the word integral. And they'll use it to mean antiderivative, they'll use it to mean indefinite integral, and they'll use it to mean definite integral. And the thing is, you have to know from the context of the problem that you're working on which thing it is that they're referring to. So that can be frustrating if you are still kind of shaky with these things, and then you're working with people who are a little more comfortable, and they're calling everything the integral, and you're kind of like, wait, are we talking about the definite integral, the indefinite integral, the antiderivative? Which is it? So just kind of be aware of that about the language. The number c is called the constant of integration. Basically, you'll all just remember it as always putting the plus c on things. The function f of x is called the integrand, and the d of x is called the differential. Okay. All right. So they tell you here, we've got these integration formulas. Now here, again, it's not always great to just memorize everything. I mean, some of these you're going to have memorized just because you're going to do enough of them. But the formulas we are about to look at, you can come up with yourself by reverse engineering the rules of the derivative. You're literally just doing it backwards. Okay, so don't spend forever memorizing all of these. Know them well enough and study them well enough that you can think your way backwards through them. That's usually a better use of time than just trying to memorize everything. Because trying to memorize a million formulas doesn't work. You're going to end up getting some of them wrong. So they tell us the following integration formulas are constructed by reversing the differentiation formulas we already studied. You should notice that each one can be proved simply by taking the derivative of the indefinite integral and showing the integrand results. In other words, and this is a great way to check your work, if you are finding the antiderivative of something, then to check your work, all you have to do is take the derivative. And if you get what you started with, then you did it right. Okay, that's great. And a lot of people don't use that, but man, it's nice on a test when you're answering some question and you're like, I don't know if I did this right. Take the derivative. Does it match what you started with? Yeah, then you should be good to go, right? So it's worth a couple of seconds to do that. So let's work through some of these and try to make sense of these. So the integral of a constant. If k is any constant, then the integral of k dx is kx plus c. So think about it. What would the derivative of kx be? Like, what if it was 3x? What's the derivative of 3x? It's 3. So what's the antiderivative of 3? 3x and then plus c. So you're literally just doing the derivative backwards. If you're comfortable with your derivative rules, think about how to do them backwards. Now, sometimes people get confused about how to do things backwards, and they don't do it right. So here is the mathematical explanation for how to do things backwards. How do you reverse engineer something? Because some people think, oh, you just reverse the order of your steps, or you just do each step backwards, and the answer actually ends up that you do both. So in mathematics, there's a principle called the shoes and socks principle, and it just helps you remember how to reverse engineer things. So let's say you get up in the morning, you're leaving the house, you're going to go out to wherever, and you need to put on your shoes and socks. So most people do that by putting on their socks first, and then you put on your shoes second, right? It would be weird to do it the other way around. If you put your shoes on, then you put your socks over your shoes. That doesn't make any sense, right? So you put your socks on first, then you put your shoes on. Okay, so now think about it. At the end of the day, when you get home, how do you undo that? How do you reverse engineer the process of where in the morning you put on socks and then you put on shoes? How do you do it? You reverse each step, and then you reverse the order, right? Because in the morning, you put your socks on and then you put your shoes on. When you come home, you can't take your socks off and then take your shoes off. How do you take your socks off if your shoes are still on, right? So you have to reverse each step, which is in the morning you put socks on, so at night you put socks off. In the morning you put shoes on, so in the afternoon or the evening you take your shoes off, but you also reverse the order. If the shoes were the last thing to go on, the shoes have to be the first thing to come off. And if the socks were the first thing to come on, the socks have to be the last thing to come off. So it's called the shoes and socks principle because if you try to explain it abstractly, people they get really confused. But if you just say, think about how you put your shoes on and off, they go, oh, that makes sense. You reverse each step and then you reverse the order, just like with my shoes and socks, right? So hopefully that makes sense. And by using that, you can work your way through all of these problems. You can reverse engineer your way through it. In fact, you can reverse engineer your way through just about anything, thinking of it that way. So think of it this way, the integral of a power function. Okay, so how do we take the derivative of a power, right? So like when you're doing a polynomial and you want to take the derivative, what do? You bring the constant down in front, you multiply by, the exponent, you multiply by the exponent. That's what happens when we're writing that number out in front. We're really multiplying by that value, right? And then you decrease the value by 1. So if we apply the shoes and socks principle to that, so we reverse each step and we do them in the reverse order, well, the reverse of multiplying by the exponent and decreasing by 1 would be increasing the exponent by 1 and dividing by that. Okay, so that's where this comes from. The integral of x to the r dx, we increase the exponent by 1 and we divide it. And what would happen if you took the derivative of this? You would multiply by r plus 1, canceling this thing on the bottom. Then you would subtract 1 from the exponent, giving you just r. So you see, once you're comfortable with that shoes and socks principle, you can work your way backwards through any of these. So you don't have to memorize like 20 formulas. Just sort of be familiar with them, and then if you're kind of forgetting, be like, wait, so how would that be the reverse of the derivative rule? And then you just work your way through it. So you'll all get comfortable with this pretty quickly. People master this part pretty well. The integral of a constant times a function. This is pretty nice. This is just like with derivatives. So this says if we have a constant times a function, we can just pull the constant out in front and then worry about the derivative part. A lot of times with these calculus problems, the key is to simplify them down, break them down, right? What do we do? Like, you probably don't even think about this anymore, but when you take the derivative of a polynomial, what are you doing? You're breaking it down into each term of the polynomial, right? You probably don't take like the derivative of the whole polynomial at once. You kind of go through it term by term. Well, what are you doing? You're breaking the big problem of the whole polynomial down into smaller pieces and taking the derivative of those smaller pieces. That's what we're doing here. We're simplifying the part that we have to take the derivative of, because, you know, even though I explained the shoes and socks principle, it can be weird trying to think backwards through a problem, trying to reverse engineer it. You're thinking your way backwards through how something was done. It's confusing. So you want each step to be as simple as possible. Well, one way we do that is by pulling the constants outside of the problem, and then whatever's left inside is a little bit simpler to deal with. Right? That's one of the keys to doing the math. Also conveniently, if we have the integral of a sum or difference, just like we do with polynomials for derivatives, you break it up into the individual pieces. So just like we take the derivative of a polynomial one term at a time, we will take the antiderivative of a polynomial one term at a time. We get to use that same property, which is really convenient, right? It means we break it down into these small pieces and we just take whatever derivative we can. The integral of an exponential function. Well, this one's pretty easy, right? If the derivative of e to the x is e to the x, then guess what the antiderivative of e to the x is? It's e to the x plus c, right? We got the plus c on the end there. So that one's pretty straightforward. The natural log of x is slightly tricky because you have to think about your positives and negatives. Remember, we can't take the natural log of a negative. So remember, we learned earlier today that the derivative of the natural log is 1 over x. So the integral of 1 over x is the natural log, except we have to make it the absolute value, and then we have our plus c, right? The absolute value is so that we aren't taking the natural log of any negatives. Oh, yes. Indefinite integrals with initial conditions. So this seems confusing to people, but it's actually not bad. It's like one extra step that you do on the end of the problem, and it's not even a difficult one. It's like algebra. The extra step to do these initial conditional problems, algebra. Okay. So what do we have going on here in a problem like this? So it says, if we have the function, find the function if f prime of x, so if the derivative is 3x squared minus 4x plus 2, find the antiderivative, but we also have been given some additional information that f of 1 is equal to 4. So what did they really just give us? They gave us an x and y value for the function f, right? The thing in the parentheses is an x value. The thing over here is a y value. So what they gave us was extra information that we can use to solve for this particular c, right? So think about it this way. What if we had this problem over here where I said, let's say I said, find the function whose derivative is 2x and passes through the point. So if I said, if I stopped there and said, find the function whose derivative is 2x, you'd go, well, there's an infinite number of them. Look, you got 3 of them on the screen right now. And I'd say, that's right. So let me extend the problem. Find the function whose derivative is 2x and goes through the point 1 comma 4. Okay, well, if it goes through the point 1 comma 4, oh, it's this one. It's this purple one right here. Well, that's basically what the problem is that we're looking at. They're telling you to find the antiderivative, so you find the family of antiderivatives. That's what they're doing here. They're reverse engineering the derivative for this, that this is the derivative of. So they're working backwards, right? Increase the exponent by 1, divide by that new number. Here, increase the exponent by 1, divide by that new number. Here, increase the exponent by 1, so it becomes x to the 1. And then we end up with the plus c. But now using this additional information that they gave us, this extra xy pair, which is essentially a point, we can solve for c and figure out exactly which function it is. Not the infinite family of functions. We can figure out exactly which one is the one that fits our conditions. So then what you do is you take the function that you just figured out, right? Your antiderivative with your plus c on the end. And then you take this x and this y pair that were given to you in the problem and see what they did. They plugged in 1 wherever there's an x. And f of 1, well, that's a y value, right? So that's where the 4 goes. So the 4 goes over here where your y value goes. You plug in 1 for x, and all you have to do is solve for c. Look how easy this math is right here. It's like additions and subtractions. That's not very difficult compared to what you've been doing, right? So you solve all this down, and you get c equals 3, and you go, oh, c is equal to 3, so that means that our function, instead of writing plus c on the end, we can write plus 3. So most of the time, you're going to be finding the family, the antiderivative family, where you have your plus c on the end. But sometimes you're going to have problems where they give you a little bit extra information, and you have to pick out then exactly which one function is the one that matches your problem. Because it kind of makes sense, right? If you're running a business, you don't want to have an infinite number of profit functions. You want to know what's the exact profit function that matches my business, right? What's the one that we care about? So that's the idea. So then they carry through with a marginal cost problem. All right, and then you're good there. So let's just double check by looking at some of these. So it looks like some antiderivatives. Okay, so here's one, question number 6. Find f of x if, so you have to find the antiderivative of this. Let me make it bigger. You're going to find the antiderivative of this, and then notice, oh, they gave me some extra information. They told me that f of 2 is 9. So 2 is my x, negative 9. 2 is my x, negative 9 is my y. So once you take the antiderivative and you have your plus c, you plug in 2 for x, you plug in negative 9 for y, you solve for c, and then you get the whole thing. So notice how in this problem there's no c. So it's really important up here when you're doing these, like they even say, use capital C. They're reminding you to do it. And in the answer, there's a plus c in your answer, right? But then down when we get to this one, there's no plus c in this one because you figured out that plus c was plus 3. So make sure you know the difference between those two questions that you're being asked. When you're doing this one, it's a marginal cost function. I would just look up that example in the book and try to follow along with what they did, right? Yeah, I guess there's only 8 questions in this first one. Find the antiderivative of this function. Yeah, so you know how to do those. So those are antiderivatives. That's our introduction to integration. We will continue with chapter 5 next week. So those of you who are ahead or totally caught up, feel free to start 5.1. I think you'll be fine working through 5.1. We basically said what we needed to say about it. You should be able to complete that. Those of you who are currently behind, get yourself caught up immediately. This is the best part of the course to get caught up. Between now and Tuesday, you'll have some time to get caught up. Once we hit Tuesday, this course is just going to move very fast until we're done, right? Because we're going to start cranking through chapter 5. The topics in chapter 5 are not small. This first one wasn't too bad. 5.1, if you can sort of think about things in the right way, 5.1 is not too bad, but it picks up and it gets more intense. And then we're going to have chapter 6 at the same time that you're taking your final exam, and then the class is over. So it's going to move real quick. Anyone who still needs to take the exam, you got till tomorrow, and then there's no taking it after that. There's no, whether it's a legit reason or whatever, you've had 2 weeks to get it done. So make sure that you get that taken care of. Otherwise, that should do it. I don't want to start anything new now with our time remaining. So as always, I'm going to shut down the YouTube stream. I will hang out in Zoom until people have no longer asking me questions. Otherwise, have a safe weekend. It's kind of warm right now. Try not to get too warm. And like I said, try to get caught up on everything. Okay, everybody, thanks. We'll see you later.